You are listening to The Vocal Technologist. Spoken tech for your ears.
What if I told you that writing code faster is actually making your entire engineering team, well, less productive?
It sounds completely backwards, does it not? I mean, we have been conditioned for years to believe that speed and raw output are the ultimate markers of a successful team.
Yeah, exactly. And honestly, it is a bit of a controversial opinion to drop straight out of the gate, but we really need to pull apart this massive obsession the tech industry has with just, churning out lines of code.
We really do. It is causing heaps of invisible problems.
Right. So I am your resident vocal technologist, your tech-savvy mate here, to help you understand complex engineering trends without you having to sift through mountains of documentation. Our mission for this session is to look under the hood of why building things too fast is actively breaking them.
Spot on.
We're also going to explore how we are attempting to put strict guardrails around AI agents and why eliminating human bottlenecks is the actual secret to genuine speed.
And I am here to help connect those technical dots. Because when you look closely at the underlying systems, the symptoms we are seeing, things like bloated code bases and fragile infrastructure, they all point to a fundamental misunderstanding of what productivity actually is.
All right, so let us unpack this first major illusion. There is a brilliant argument circulating that code generation is simply not productivity.
It really is not.
For the longest time, managers have judged developers by how many lines of code they commit. But lines of code are a genuinely terrible measure of success. Programming is not really about typing fast, is it?
No, not at all. It is about understanding complex business problems and managing system complexity. If we connect this to the broader picture, the rapid introduction of large language models has completely warped our sense of progress.
Yeah, it feels like everyone is just racing to type as much as possible.
Exactly. These models accelerate the raw writing process immensely. But what happens when you type faster than you can actually think through the architectural implications? You get premature implementation. You get solutions to the completely wrong problems.
Yes, exactly. You get massive amounts of just unnecessary code. It is like, imagine having an automated bricklaying machine on a construction site.
Okay, I like where this is going.
Right, so imagine this machine can build brick walls instantly, like 100 times faster than a human crew. But it has no real blueprint, so it just builds them in entirely the wrong places across your site.
Oh, wow, yeah.
You end up spending all your time and energy knocking those walls down just so you can, walk through the front door of the building.
That is a brilliant way to put it.
Yeah.
Because it perfectly illustrates the mechanism of the problem. What that AI bricklaying machine is actually generating is maintenance debt.
Exactly. Maintenance debt.
You are taking the heavy cognitive costs away from the initial writing phase, and you are dumping them squarely onto the maintenance and comprehension phases. The AI spits out a massive block of logic in 2 seconds, right?
And then what?
Then a human engineer has to sit there for 3 hours trying to understand the nuanced decisions it made.
Yeah.
Or, more dangerously, the edge cases it completely failed to consider.
It is genuinely amusing in a slightly painful way. We built these incredibly complex tools to save time, and they are creating a mountain of debt that eats up all the time we supposedly just saved.
It is a massive irony.
It really is. It feels like we are just shifting the bottleneck from the keyboard to the reading glasses.
Which is exactly why true productivity requires critical thinking. The output we should be measuring is problems solved and complexity reduced, not just a high volume of typed characters.
Absolutely.
An elegant solution might be 10 lines of code that took 3 days of intense whiteboarding to design. That is so much better than 1,000 lines generated in 3 seconds that takes your entire team a week to debug.
Right. I completely agree. So if letting AI write endless code wildly is dangerous, how do we constrain it? Because let us be real, you and I both know nobody is going to stop using AI.
No, the genie is well and truly out of the bottle.
Exactly. So we have to box it in. We have to give it strict, unbreakable rules.
This brings us to the crucial concept of isolation. We're seeing tools like Claude Code integrating directly with Docker. This allows developers to use local models and connect to over 300 model context protocol servers.
Hold on, let me just clarify that for anyone listening who has not messed with it yet. The Model Context Protocol, or MCP, is essentially a standardized way for AI to talk to external data sources and tools, right?
Yeah, that is correct.
It gives the AI a structured way to fetch information or execute commands.
It provides the necessary context. But the critical part here is how Docker handles the execution. Docker runs these operations in highly isolated micro-VM sandboxes.
Oh, micro V.
Yeah. This means the AI agent can autonomously modify files, test configurations, and execute terminal commands without risking the host machine's core operating system or, your personal files.
Which is a massive relief. I have to admit, I have always been incredibly skeptical about letting an AI agent autonomously run commands on my local machine.
It is a valid fear.
It feels exactly like giving a hyperactive apprentice a nail gun and telling them to just go nuts in your living room. You just know a pipe is getting punctured.
That is exactly what would happen.
Yeah. But this Docker isolation is like giving that apprentice a designated reinforced sandbox out in the yard. They can build whatever weird structures they want in there, but they are physically prevented from accidentally burning down the main production factory.
That physical and logical isolation is key. And it is not just individual agents operating in a vacuum either. The Docker agent framework allows for building collaborative AI teams.
Like teams of AI.
Yeah. You can configure specialized roles. Yeah. So one agent handling UI design, another writing the back-end logic, another aggressively testing and debugging. And they all communicate within that safe, ephemeral micro-VM environment.
Okay. Having a little enclosed virtual office of AI agents arguing about testing protocols is properly wild, but it raises a big concern for me.
What is that?
How do we ensure they actually know how to deploy things correctly once their code leaves the sandbox? If they do not know the company standards, they will just make up their own infrastructure rules.
That is where opinionated defaults come into play. And they are incredibly important. DigitalOcean has introduced app platform skills, which are open source AI native playbooks.
Oh, playbooks for the AI.
Exactly. They give coding assistants highly specific, up-to-date knowledge about deploying applications to production environments safely.
Opinionated defaults are the absolute best. You really do not want the AI making naive choices about infrastructure, like leaving a database port open to the public internet just because it was the easiest way to get the connection string working.
Exactly. What is fascinating here is the mechanism behind these defaults. They're based on thousands of real-world successful deployments.
Right.
For example, the playbook enforces virtual private cloud networking by default. It insists on PostgreSQL version 16 with SSL strictly required.
Oh, that is properly locked down.
Yeah. And crucially, it instructs the AI to use GitHub secrets by name. So the assistant never handles the actual sensitive string values directly.
Oh, I love that. So the AI just knows the secret is called database password and passes that reference along, but it never actually sees the plain text password itself.
Precisely.
It is a brilliant way to handle credentials without risking a massive leak in a chat log. And it seems like the big players are trying to standardize how we manage these AI tools at an enterprise scale.
They absolutely are.
Like Microsoft has put the Azure DevOps Remote MCP server into public preview. They are moving the whole protocol to the cloud using Microsoft Entra authentication, and they are even planning to phase out local setups eventually.
It is a very natural evolution for enterprise security. By moving the MCP server to the cloud, you eliminate the friction of local developer setup.
Which is always a nightmare.
Always. But more importantly, you ensure enterprise-grade authentication is baked in from the absolute start. It is all about providing context and isolation. You give the AI the exact tools it needs securely, and you strictly define the boundaries of what it can touch through central access controls.
Okay, so let us look at where we are. We have our hyperactive apprentices perfectly sandboxed. We have secured our deployments with opinionated defaults. Our AI agents are writing code securely without touching raw passwords.
All good things.
Right. But if you look at most engineering teams, their delivery pipelines are still incredibly slow. Why? Because the bottleneck is no longer the typing. The bottleneck is the human review process.
This raises an incredibly important question about how we view quality control as an industry. The uncomfortable reality is that every additional layer of human review in a process makes delivery up to 10 times slower.
Wait, 10 times? That is massive.
It is mathematically devastating.
And look, if you are listening to this and you write code, you have absolutely felt this relatable frustration. You write a brilliant feature in 10 minutes, you feel great, you submit the pull request, and then it spends 2 weeks gathering dust in a review queue. It is agonizing.
And if we analyze that 2-week period, the vast majority of that time is spent simply waiting.
Exactly. It is not like someone is staring at it for 2 weeks.
No, it is not active review time where someone is meticulously checking your logic.
Yeah.
It is a piece of code sitting in a queue waiting for a senior engineer to have the mental bandwidth to context switch from their own work and look at it.
Right.
And AI tools do not meaningfully fix this bottleneck because the AI is not the one holding up the approval authority.
That makes total sense. The AI can write the function in 3 seconds.
Yeah.
But if Derek from security is on annual leave and he is a required reviewer, that code is not going anywhere.
Precisely. We really need to question our fundamental assumptions about how we ensure quality. Adding more mandatory reviewers feels safe. It feels responsible to management. But queuing theory tells us it completely destroys velocity.
Okay, but I have to push back here. What is the alternative? Do we just drop all manual reviews, merge everything, deploy straight to production, and hope for the best? Because that sounds like a recipe for a catastrophic weekend outage.
Not at all.
Yeah.
It is not about abandoning quality. It is about shifting how you achieve it. The real path to speed is eliminating the need for manual reviews through much better system design.
Okay, how so?
You rely on small, highly trusted teams. You build incredibly robust automated testing suites that catch regressions instantly. And most importantly, you focus on continuous root cause improvement.
Right, so fixing the actual system.
Exactly. When a bug happens, you do not just add another manual checklist step. You fix the system so that a specific class of bug is prevented systematically. You stop relying on a tired human to catch things late in a review cycle.
So it is about trusting your automated architecture over trusting a manual human checklist, which actually perfectly mirrors how some of the biggest tech players are handling their actual system architectures.
Yeah, well, it is.
They are getting faster by getting smaller. It is addition by subtraction.
It is one of the most elegant principles in engineering. When you strip away the bloat and the unnecessary complexity, you gain massive performance.
I saw this statistic from Datadog, and I genuinely had to do a double take. I thought it was a typo.
A Go agent one.
Yes, they cut their Go-based agent binary size by 77%. They dropped it from 1.22 gigabytes down to 428 megabytes. And they did this without removing a single functional feature. I'm sorry, but how is that even physically possible?
Yeah, it's pretty staggering.
You do not just find nearly a gigabyte of spare change in the couch cushions. Surely they had to sacrifice performance or drop legacy support to achieve that.
It sounds impossible, but it comes down to incredible technical discipline and understanding exactly how your compiler works. They achieved this massive reduction by ruthlessly auditing their dependency trees.
Okay, that makes sense.
But the real magic was in 2 specific areas: isolating optional code using build tags, and minimizing the use of reflection in Go.
Okay, let us break that down for the listener. Reflection in Go is essentially a feature that allows a program to inspect its own variables and structures while it is running, right? But what does that have to do with file size?
Excellent question. To allow a program to inspect itself at runtime, the Go compiler has to pack a massive amount of type metadata into the final binary.
Oh, like a giant dictionary of everything inside the program.
Exactly. If you redesign your code to minimize or eliminate reflection, the compiler can strip out all that heavy, unused metadata because it knows the program will not ask for it later.
That makes total sense. And the build tags.
Build tags tell the compiler to only include certain files if specific conditions are met. Instead of compiling every single integration and feature for every possible environment into one giant monolithic binary, the build tags ensure that if you are deploying to Linux, the Windows-specific code is completely ignored during compilation.
So it is less like cleaning out a messy garage where you realize you own 3 identical lawnmowers and more like packing a highly modular suitcase.
On.
Instead of dragging your heavy winter coat, your scuba gear, and a full tuxedo on every single trip just in case you might need them, build tags, let the system look at the destination, and only pack the exact tools needed for that specific environment.
That's a perfect analogy, and we see the exact same philosophy paying dividends in the Kubernetes ecosystem. The Kubernetes team rewrote a critical internal tool called kpromo. It is their image promoter that handles verifying and moving every single container image published to their official registry.
That is a massive critical job. If that breaks, the whole ecosystem feels it. So what did they do?
By rewriting it, they reduced the total code base by 20%. But the performance impact was staggering. Their production promotion jobs went from taking 30 minutes to complete down to between 2 and 15 minutes.
That is absurd. You delete 20% of your code and your system suddenly runs up to 15 times faster.
But what was the actual mechanism there? What was the old code doing that made it so slow?
The old codebase had accumulated layers of sequential synchronous API checks. It was doing things one by one. verifying enormous lists of images in a very linear blocking fashion.
Ah, so just waiting in line constantly.
Right, by stripping out the bloated legacy logic and rewriting it with modern concurrent patterns, the system simply had less unnecessary work to do. Less code literally equaled less wasted compute cycles. It proves that less code equals more power.
It really does. And it is not always about massive, dramatic overnight rewrites either. Look at the Python 3.15 JIT compiler.
Yes, that is a great example. The community has been trying to speed up Python for years. They finally achieved real measurable speedups, around 5 to 12% on average. But it was not from one magic algorithmic breakthrough that someone invented in a weekend. It was highly iterative, community-driven development.
Yes, and the mechanism they focused on was trace recording and reference count optimizations. Trace recording is a fascinating technique.
How does that work?
Instead of trying to optimize the entire program at once, the system watches the code as it runs, identifies the hot paths, which are the specific sequences of instructions that are executed most frequently, and then optimizes just those specific traces.
It is the unglamorous, meticulous work that makes the biggest difference. Auditing dependency trees, rewriting linear API calls, cleaning up trace recordings.
Yeah.
But here's where it gets properly interesting. When you finally nail that system design and you trim all the fat, you achieve incredible scale and stability. But maintaining that massive scale requires an almost obsessive understanding of robust infrastructure management. You have to know the granular nuts and bolts of the systems running your lean code.
You absolutely do, because massive scale does not happen by accident, and it certainly does not sustain itself without deep observability.
Let us talk about Amazon S3 for a second. Over its lifespan, it has grown from storing 1 petabyte across 400 nodes to holding over 500 trillion objects. It handles 200 million requests per second.
The pure engineering discipline required to handle 200 million requests every single second without catastrophic systemic failure is difficult to overstate. It requires an architecture that is fundamentally resilient to hardware degradation.
It is like a massive automated warehouse that never ever stops expanding. But the craziest part to me is that AWS dropped the pricing by 85% over that time, from 15 cents to just over 2 cents per gigabyte. And it maintains total backward compatibility. Code written against the S3 API 20 years ago still works flawlessly right now.
If we connect this to the broader infrastructure picture, maintaining that kind of operational excellence requires deep, granular visibility into your resources. You cannot manage what you cannot measure.
Right.
Which is exactly why modern engineering teams are so focused on very specific metrics. Take Carpenter, for instance, which is an open source node provisioning project that handles Kubernetes auto-scaling.
Right. Auto-scaling is basically the magic trick that keeps the lights on and the servers from crashing when your app suddenly goes viral and traffic spikes.
Exactly. But you cannot just turn Carpenter on, walk away, and assume it will magically handle everything.
Yeah.
You have to actively monitor it using Prometheus metrics.
What kind of metrics?
You need to track provisioning latency, which is how many seconds it actually takes for a new node to spin up and become ready to accept traffic. You have to track consolidation activity to ensure the system is packing workloads efficiently, and you are not wasting thousands of dollars on underutilized virtual machines.
And you mentioned API throttling earlier, which sounds like a silent killer for auto-scaling.
It is. You must monitor API throttling. Because if your cloud provider decides you're making too many requests and starts rejecting your API calls, your auto-scaling simply stops working. Your app will crash while Carpenter silently fails to provision the nodes you desperately need.
Okay, I hear all of that, but let me play devil's advocate for a moment. What does this all mean for the developer on the ground who just wants to write features?
That is a fair question.
These granular infrastructure details seem so disconnected from actually writing application code. Like, take Kubernetes pod restarts versus pod recreations.
Yeah.
I see developers arguing about this. Why does that highly specific distinction matter so much for a developer trying to troubleshoot a broken system at 2 in the morning?
It matters immensely because it dictates how you diagnose application state. The critical difference lies in the pod UID, which is its unique identifier.
Okay.
If the pod UID changes, Kubernetes has performed a complete recreation of that resource. It is an entirely new entity. From the cluster's perspective, it might be on a completely different physical node, and the restart counts reset to 0. But if the UID stays exactly the same, It is just a container restarting within the existing running pod.
Oh, I see. Okay, so if I am looking at my dashboard at 2 a.m. and I see 0 restarts, but my application has been flapping and dropping connections all night, it might be because the whole pod keeps getting violently recreated by the scheduler rather than just the internal container bouncing.
Precisely. If you do not understand that specific infrastructure mechanism, you will look at the wrong metrics, you will assume the container is stable because the restart count is 0, and you will completely misdiagnose the failure.
Wow, yeah, that would ruin your night.
It would. Understanding these granular details is the foundational bedrock that allows massive scale to function smoothly.
It really is all interconnected. You cannot just write the code. You have to know where it lives. And the security side of infrastructure is getting just as granular. There has been a lot of movement with these CRIO credential provider plugins. They enable secure Kubernetes authentication to private registry mirrors so your cluster can securely pull the container images it needs. And they do it using namespace scope secrets.
That is a crucial development for multi-tenant isolation. It solves a massive security headache.
Yeah, for those managing multi-tenant clusters, you know the absolute nightmare of node-level credentials. It is terrible practice.
Yeah.
CRIO is fixing this by essentially generating temporary single-use VIP passes for each specific namespace, rather than giving out a permanent master key to the whole building.
That is exactly how it works. Instead of relying on node-level credentials, which grants dangerously broad access to everything on that node, the QLit uses these provider plugins to retrieve secrets dynamically via service account tokens.
So it is just on-demand access.
Yes. It generates temporary, short-lived authentication files just for CRIO to use. This means if one single namespace is compromised by a bad actor, it does not jeopardize your entire cluster's registry access. The blast radius is tightly contained.
It is all about limiting the blast radius. We are seeing this push for granular security combined with simplified management absolutely everywhere. The cloud providers are stepping up to abstract the hardest parts.
They are, yeah.
Like Azure Databricks serverless workspaces are doing 0 configuration deployments now, where data teams can get fully managed, secure workspaces running in minutes without ever touching custom networking rules. Oracle Cloud Infrastructure has introduced OCI database management for unified Exadata monitoring across complex multi-cloud environments. It is all about giving developers deep visibility without making them manage the raw iron or configure the underlying networks.
And that brings our entire discussion full circle. By relying on cloud providers to abstract the heavy lifting of infrastructure, by sandboxing our hyperactive AI tools so they cannot break things, and by aggressively reducing bloated code bases through smart dependency management, we are fundamentally trying to clear the path for engineers to actually engineer again.
To sit down and solve complex human problems rather than just managing the endless complexity of their own tangled tools. Which leaves us with a totally different, rather provocative thought to mull over. If AI is rapidly building all the boilerplate code and automated frameworks are perfectly managing and scaling the infrastructure, the next great tech divide will not be between who can write code and who cannot. It will be between who knows what high-level architectural questions to ask the system and who is just blindly taking orders from it. Keep that in mind next time you are staring down a completely untouched review queue. I am your vocal technologist, keeping it punchy and thoroughly unpacked. Catch you on the next one.
Spoken Tech for your ears.